Hey everyone, my name is Kevin Wu, and today's topic is how to use calculus to optimize your soda can. And let us begin. Understanding the problem. This can of soda contains a volume of 500 milliliters. What is the minimum quantity of aluminum needed to package the soda can? So we're gonna modify the problem. Let's write down the surface area of the soda can and the volume of the soda can. So the area equals 2 pi r squared plus pi r h, and volume is pi r squared times h. How I got this equation, basically, you have two circles up, the one from the top and one from the bottom. That's why the 2 pi r is here. 2 pi r squared. Pi r h, 2 pi r h is the area that wraps around the can, right? If you expand that, you get a rectangle, and the length is just the circumference of the circle, and of course the width is just the height. And the volume is pi r squared times height, and 500 milliliters is the same as 500 cubic centimeters. That is a really great realization there. So now we're gonna simplify this the system of two equations by using substitution. Earlier we know that v equals pi r squared times h. Now we're gonna replace the v with 500, and solving for height, we get 500 over pi r squared equals height. Now we can replace the h in our area equation with 500 over pi r squared. The reason why we want to do this substitution is because we want to minimize our area, right? So therefore, we want to have everything in terms of our area equation. So now we have, okay, you see that the pi r cancel out with the pi r squared. You multiply the 2 with 500. So our final equation is a equals pi r squared plus 1,000 over r. This equation gives you the surface area of the soda can for any given radius. Now we plug in this equation into decimals, and remember that you're going to replace a and r with x and y, or y and x, in order for decimals to read it. So you see this graph, we want to find the local min here. So in order to do that, we got to differentiate a. So differentiate that gives us 4 pi r minus 1,000 over r squared. Those are just basic power rules. Then we solve this in terms of r. No, we first set it equal to 0, because when you find your critical points, you're going to set it equal to 0. Then solve for r. So r turns out to be 4.301. Now this radius will give the minimum packaging. Okay, that is our ideal radius. Now we have the radius, we can therefore solve for the height and surface area. So using this equation, height equals, plug in the radius, we have h equals 8.604, and using our previous area equation, we plug in the radius found earlier, we get our surface area is 348.7. So these are the dimensions that will give us the least amount of material in order to package a soda can that contains 500 milliliters. So part A solved. Now, part B, we added a magical twist. Basically, a wizard spells some of his magical liquid onto this can, and now the can's radius is expanding at a rate of 3 centimeters per second, and its height is decreasing at a rate of 4 centimeters per second. At some instant, the radius is 5, and the volume is 785.4. What is the rate of change of the volume at this moment? So we're gonna start. So for any related rates problem, we always want to start with writing down what we know. So we know dRdt, we know dHdt. It is so important to know that when something is decreasing at a rate, although that rate is not right in a problem, it didn't say that the rate is negative, but when you actually write dHdt, you gotta make it negative, right? Because it's decreasing. And now, in that specific moment, we have the radius, we have the volume, we can solve for height. So using the volume equation, we found out that the height is about 10. Okay, so we can find dv dt by plugging in the values. So previously we said v equals pi r squared times h. Now differentiate that, plug in everything we know. Okay, by the way though, here is some implicit differentiation, right? Because you're differentiating everything in terms of t. So when you're done with the 2 pi r, you want to make sure to have the dr dt afterwards, and the same applies to the h. And of course, you have everything. You have dRdt, you have dHdt. We solve for h, you know your radius. You just plug in this whole chunk into your calculus, and dv dt should be 628.3. So part B is solved. And part C requires us to use the integral formula for arc length to prove that the circumference of a circle is indeed 2 pi r. So you can imagine that we cut the cylinder in like perpendicular. We cut the cylinder and the cross section is the perfect circle. So we want to find the arc length without using 2 pi r. So we know the arc length formula. We know the circle equation. So I'll walk you through my proof. So we know the givens, right? Now you want to isolate y. Y equals the radical of r squared minus x squared, and you want to differentiate this by rewriting the radical as 1/2, and then this is just power rule, then chain rule. Then you want to square this. Now this becomes x squared over r squared minus x squared. Now you plug this in to our integral. By the way, for the a and b, for the bounds, I just treated this as like a polar function, and I went from x equals r to x equals 0. And then I multiply this by 4 because, from x equals r to x equals 0, you're only getting 1/4 of the circle. But we want the entire circle, so you want to multiply that by 4, which is a classic technique used when you're finding the polar areas on BC Calc. Okay, so and the rest of this is just algebra. You rewrote the 1 as r squared minus x squared over r squared minus x squared. You cancel out the x squared, and then you factor out the r. You get 1 over the radical of r squared minus x squared, and this is indeed the formula for arc sine. So now we have 4r times arc sine of x over r from 0 to r, right? Upper minus lower. So arc sine of 0 is 0, and arc sine of r over r, which is the same as arc sine of 1, is 1 because is pi over 2, because sine of pi over 2 is 1. Okay, so what we have left is just arc length equals 4 pi times minus pi over 2 gives us minus 2 pi r. But some of you are probably wondering, the circumference of the circle is 2 pi r, not negative 2 pi r, and you're indeed correct. Because there's one thing that we didn't do, which is flip the bound, right? Because your radius is never going to be 0 and is never going to be less than 0. It's always going to be some positive number. So therefore, your lower bound cannot be less than your upper bound. So we have to flip this, and therefore adding an extra minus sign in front of it. So which is the same as making this minus sign a positive sign. So therefore, we just proved that the circumference of the circle is indeed 2 pi r. Yep, and that's it. Thank you for watching, and remember that calculus is amazing.